All right, Honors Chem, today we are going to still be talking about energy, but instead of energy of a reaction, we're going to be talking about energy of electrons. Now, back when I first started teaching, we used to do this chapter in the middle of our atomic theory lesson so that we could see how this came around with one of the atomic models. And one of the atomic models we talked about a little bit in our atomic theory was the Bohr model. And this arrangement of the electrons in the atom and how these electrons jump from one area of an atom to another, we've already done quantum. So we know that there are shells and subshells. But back then they didn't really know that there were shells and subshells, so they thought they were more of a planetary model where we had orbits. You'll see why they thought that we had orbits here in a minute. Okay, and we're going to talk about the energy that we see off of those jumps. Okay, so here we go. It's going to feel like a little bit back into atomic theory here. So after discovering 3 subatomic particles in the early 1900s, scientists continued their quest to understand the atomic structure and the arrangement of the electrons in the atoms. Okay? So in order to do this next thing, we have to understand a little bit of physics. We have to understand some light and how light works. So to understand further advances in this atomic theory, we need to have a light, quote unquote, discussion of the nature of light. Okay, little pun there. There are 2 variables that relate to a beam of light or a wavelength of light. So these variables are wavelength, and we designate wavelength with the Greek letter lambda. This is lambda. Lambda. Okay, it's kind of like an upside down Y. Okay, and the other variable that we use is frequency, and we designate frequency with nu. So nu is kind of like a V where one side is straight and the other side is kind of curved, like a U. Looks kind of like a seagull off in the distance or whatever. So we have lambda and we have nu. And you might want to practice writing these a little bit, okay? So here we go. Let's look at a wave. So we normally see a wave like on the ocean, and we see it going up and down, and we see it moving through time. Let's take like a snapshot, okay, of a cross section of the wave. We have the peaks right here, and they're sometimes called crests, and we have the bottoms, which are called troughs, okay? The amplitude is how high it is. So if we were like on a surfing day, we'd want some big waves. We'd want some amplitude. If we were just boogie boarding, we don't need a lot of amplitude. We could have some small waves. Okay. Now, if I measure from crest to crest, this will get me the wavelength. And this can usually be done in meters. Sometimes we will do it in centimeters, nanometers, even picometers, depending on how big or small that wave is. Okay? Now, we don't have to just measure it from trough to trough. We can measure it really, the wavelength, from any same point on the wave. So I could measure it from trough to trough, crest to crest. I could measure it also from here to here, or I could even go from here, let's see, 1, 2, 3, to here. Okay, just as long as I'm in the same spot of the wave where I start and I cut it off, that will give me the wavelength. Okay, so let's look at this really quick. So when we do our math with the waves, we have to take into account both wavelength and frequency. So let's take a little bit of a talk on frequency here. So frequency is just the number of cycles of waves that go through a specific spot per second. Okay? So frequency equals number of wave cycles per second. Okay? So we're going to pretend that this line, both of these lines, last 1 second. And this one's going to last 1 second. So I want you to count how many wave cycles we have. Let's look at this red one first, okay? So here we go. We've got 1, 2, 3, and 4. So our frequency would be 4 per second. And we can always do cycles if you want to. Now there's another unit that we use instead of just per second. This also reduces down to Hz, which is hertz. You might have heard hertz on, if you listen to the radio. Our radio frequencies are megahertz. So 1,000,000 hertz, 1,000,000 cycles per second. So the actual call number of that radio station is how many megahertz for the FM or kilohertz for the AM that there are in that radio wave per second. Okay, let's look at this purple one. How many cycles do we have in that 1 second? I want you to take a minute. Okay, did you figure out we have 1, 2, 3, 4, 5, 6, and 7? We have 7 cycles per second on this one. Or this would be 7 hertz. We could also say it like that. Now I want you to notice something. Notice as our wavelength gets shorter, do you see how this one has a shorter wavelength than this one? Our frequency goes up. So frequency and wavelength are inversely proportional to each other. So frequency is inversely proportional to our frequency. When wavelength gets big, our frequency gets really, really small. When frequency gets really big, our wavelength gets really small. Okay? So here we go. Let's do some math here. Let's generate an equation or two. So when we do this, our wavelength, which is in meters, right? And our frequency, actually, I need to put that in another spot. Our wavelength, which is in meters, and our frequency, which is in per seconds. So what happens if I have meters times per second? I get a unit of meters per second. What is meters per second? Isn't that a speed or a velocity, right? This gives me a speed or a velocity. Okay? And guess what? That speed is c. If you've ever done physics, c is the speed of light. Okay? So the value of the velocity of light or the speed of light is 3.00 times 10 to the 8th meters per second. Okay? Or 3.00 times 10 to the 10th centimeters per second. It's a constant. Okay? So if you know velocity and the wavelength, you can get the frequency, right? If you know the frequency and the velocity, you know you can get the wavelength because the velocity is constant. So really, if I know frequency, I can get the wavelength. If I know wavelength, I can get the frequency. Okay? All right. So here's our equation then. So the speed of light is equal to our wavelength times our frequency. That means wavelength is equal to speed of light divided by frequency, and frequency is equal to speed of light divided by wavelength. Okay? Remember that c is 3.00 times 10 to the 8th meters per second. Now you are going to want to keep that constant in your head. Okay? All right, let's talk about how we use this electromagnetic spectrum to talk about these different waves. Now, the electromagnetic spectrum, we're used to seeing light, but light, the visible light that we can see with our eyes, is really just a small portion of the electromagnetic spectrum. So here's kind of a graph on this, and I'm going to open this up a little bit longer. Notice that our visible spectrum is just a tiny little portion of this. All the things that we see makes up a very small portion of the electromagnetic spectrum. Okay, so let's go down to the longest wavelength, so lowest frequency things. We start with radio. Radio are our longest wavelengths. Okay, notice their wavelengths can be tens of thousands of meters long, right? So we have our AM frequencies and our FM frequencies are a little bit shorter, okay? And then we have our cell phone frequencies are about here. Then we have microwaves, things that we use to cook our food. And then we have infrared. I don't know if you've ever stood under an infrared lamp or ever been at a fast food place where they have like the burgers and the fries under a lamp. That lamp is infrared. It feels hot. So this feels warm. Our bodies sense infrared by heat, okay? And then we have our little part of the electromagnetic spectrum that is visible light, and that's all the things that we see. And then we have ultraviolet here, which is a little bit shorter wavelength than our visible light, our X-rays, and our gamma rays. So everything from ultraviolet up here, this is what we call ionizing radiation. These wavelengths above visible light actually have enough energy. As we go up here, as we get higher and higher, our energy increases. Okay? So ultraviolet on, the energy is so much on these waves that come through that they actually have enough energy to take an electron that is in one of these orbitals in an atom and knock that electron off the atom and create an ion. And that's why we call it ionizing radiation, because it has enough energy to knock an electron off the orbital and cause an ion. That is what causes mutations in our cells. So if we have a random UV or a random X-ray or random gamma ray coming from the sun or a radioactive whatever, we can have an electron be knocked off of one of the atoms in our cells. And if that atom so happens to be on a DNA molecule that so happens to be a gene that expresses an on or off sequence to a gene, we can have some serious problems. This is how cancer gets started. Okay? So it's really important, you know how your parents have always told you when you get out in the sun, wear sunscreen? Yeah, wear sunscreen, because that ultraviolet rays, the stuff that causes your sunburn, actually causes mutations. That's why, sunburn is really a radiation burn. Okay? All right. So we're going to use this equation where we have the speed of light is equal to lambda nu. Okay? So wavelength times frequency to see what the frequency of a beam of red light is. Okay? So you are definitely going to want your calculator, and this unit, we're going to use our units, our metric units a lot. So you might want to revisit your metric units a bit. Okay? So here we go. I want to isolate frequency. So frequency is going to be equal to the speed of light divided by our wavelength. So our speed of light is 3.00 times 10 to the 8th meters per second. So we've got C, and our wavelength is 765 nanometers. Now, notice this is in meters, so we've got to get our nanometers into meters. So nano, do you guys remember how many there are in nano? There's a billion. So there's 10 to the 9th nanometers in 1 meter. Okay, so my nanometers are canceled. I now have meters that can cancel. Now I have just per second, which is what I want for frequency. Okay, so when I do that, I've got 3 sig figs here. So that will give me 4.44 times 10 to the 14th per second. I could also write this as 4.44 times 10 to the 14th hertz. Remember, hertz is just another way of saying per second. Okay, let's do this next one. What is the wavelength of ultraviolet radiation with a frequency of 2.7 times 10 to the 14th per second? Now remember that per second can also be listed as hertz. Okay, so I want to isolate wavelength. So C equals lambda nu. And if I isolate wavelength, wavelength is C divided by nu. So here we go. We've got our speed of light, which is C, 3 times 10 to the 8th meters per second. And we're going to divide by 2.7 times 10 to the 14th. Now, remember that -1? It actually means this is per second. So that means if I flip it, that means the seconds go on top. So the seconds will cancel out and I'm left with meters, which is what I want, right? So 3 times 10 to the 8th divided by 2.7 times 10 to the 14th. And I've got just 2 sig figs here. So this will give me 1.1 times 10 to the -6th meters. Okay, doing okay with that? Okay, objects get their colors from reflecting certain wavelengths when hit by white light. Light reflected from green leaf is found to have a wavelength of 4.9 times 10 to the -7th meters. What's the frequency? So you know that light from a green leaf, it's actually absorbing the red and the yellow and the orange and reflecting the green. And that's why it looks green to your eye. Okay, so here we go. So we want to find the wavelength. So wavelength, once again, is the speed of light divided by nu. So we're going to have our speed of light, 3.00 times 10 to the 8th meters per second. And we're going to divide by our frequency, which is 4.90 times 10 to the negative, or actually, no, we wanted to find frequency. I wrote that wrong, sorry. Times 10 to the -7th meters. So my meters cancel out. And I'm left with per seconds, which is what I want for frequency. I've got 3 sig figs on both of these numbers, so 3 sig figs for my answer. I've got 6.12 times 10 to the 14th hertz, or I could also write it per second. Either way, okay? So, after careful analysis, the electromagnetic wave is found to have a frequency of 7.8 times 10 to the 6th hertz. Oh wow, that went down on me. So let's rewrite this. Okay, so let's start again. After careful analysis, an electromagnetic wave is found to have a frequency of 7.8 times 10 to the 6th hertz. What's the speed or velocity of the wave? Think about that for a second. Okay, speed equals lambda times frequency. Isn't the speed of light a constant? Yeah, c is a constant. So it's 3.00 times 10 to the 8th meters per second. Okay? Don't get fooled by asking what the speed is because it's all the speed of light. All right? So that is how we use wavelength and frequency to generate different wavelengths and frequencies along the electromagnetic spectrum. This last video we're going to do is going to be about energy. So we'll see you in just a minute.